Welcome back to week 4, and we're going to continue on with groundwater. And in this video, we are going to talk about what aquifers are and what the major types of aquifers exist. And then we'll talk about hazards associated with groundwater. So what are aquifers? Aquifers are basically a body of rock that can easily transmit and store water. So it has a decent permeability and porosity to be able to hold that water and to be able to transmit it from one place to another. Aquifers that we actively use are ones that we can pump water out of. So it has to have a good permeability and porosity to be able to move that water from place to place. There's 3 major types. There's confined aquifers, unconfined aquifers, and perched aquifers. So one thing to note before we get into the types of aquifers is to talk about what groundwater is and kind of show you a little bit of what that looks like. So if we were to take a slice into the earth, here's our surface topography. We've got surface water in one part, and this blue line is showing you where the water table is. And you can see that that water table tends to mirror the surface topography. Where it's higher, the water table is close to the surface, up high. Where it's lower, the water table is again lower too. So you can see how it has that curved plane just like the surface does. And so that water table is right where you have all of the pore spaces in the rock completely filled with water. So how does groundwater move? Well, it's going to move from high elevations to low elevation. So here you can see you got high elevation on either side of this river. Rainfall seeps into the ground and then gets into the water table. So this would be an unconfined aquifer where the water just seeps in and enters the water table. So we have an unconfined aquifer here. And then transmits slowly into that stream. And that stream is actively flowing. It's a spot where it's an outlet to the groundwater. And so that stream will be considered a gaining stream. And then if we look over here, a more complex situation, what we have is, this is kind of a little bit more realistic, what we actually have in the earth. And what we see is on the surface of the earth, we've got an unconfined aquifer and then what's called a confining bed. So our aquifer is going to be a rock unit or sediment unit that has enough pore space and permeability to transmit water, whereas the confining bed doesn't have the permeability to let water through it. So it's going to hold, trap water on one side or the other. The confined aquifer is going to have those confining beds on either side. So that confined aquifer, the water gets in from someplace else and it gets basically trapped there until you drill a well into it to be able to pump the water out. And so the deeper you go, the longer it takes that water to transmit from place to place. So here's just a different scenario here. We've got our unconfined aquifer on the surface here. And this one would be emptying into this river. And then we have our confining layer, this dark brown layer. And then we have our confined aquifer. So up here would be considered unconfined because the water can easily get into that layer. But then as it transmits down into this bed, gravity's pulling it down, and because it has more material on top of it, it's under some pressure. So when you drill a well into it, the water is going to rise in the well up to a point where that pressure from this confined aquifer is going to push it up to, we call it the piezometric surface. And when we have lots of pressure on that confined aquifer, sometimes we can get wells that are flowing. Those are called artesian wells. And here's just a couple examples of a pretty calm flowing one and then a pretty crazy flowing well. So those are the different types of aquifers. It might be helpful to be able to draw or sketch one of those, a diagram that has all 3 on it. So some of the different hazards associated with groundwater. Some of the main ones that we're going to talk about are sinkholes, disappearing water bodies, cone of depression, saltwater intrusion, and pollution. So sinkholes are the first one. We kind of touched on this before. So sinkholes, here you can see some sinkholes in Florida that occurred. And these are happening because this is limestone bedrock. And in Florida, there's a lot of development. So we have a lot more houses being built, so we're adding more and more weight to the surface of the land, destabilizing the roofs of those caves. And we have a lot more people using the groundwater, pumping water out of the ground. So we pump water out, water table drops, caves get exposed, and that water was once a support to those caves. Once it's gone, caves are weakened, and so we end up with kind of a double whammy for these areas, and we can have some sinkholes developing. Pretty scary. And here, there's a great website here I'll show you. I got a lot of this information from, oops, there we go. So, a USGS Water Science School, you have a link to this, and it talks about sinkholes, what they are, shows you some great photographs, and places that are susceptible to caves and sinkholes. We're pretty safe where we are. And then kind of how these form. So here's our showing you how the caves are created. And here we've got kind of the stages. We've got places where we've got a layer of sediment on top of the limestone that gets collapsed so that sand can fill in that cave over time. You get a depression on the surface, or you can have a collapse that can happen. And then we can have man-made ones as well. So that website's great. It has a lot of awesome information on it. So I strongly suggest you take a look. Another problem is increased water withdrawals from aquifers. And this is a map here showing you, as of 2005, the total groundwater withdrawals by state. So the darker the blue, the more water is used. California, high population, pretty dry in places, lots of groundwater use. Texas, Arkansas, Nebraska, these are also areas that can be fairly dry, but also the breadbasket of the United States. This is where a lot of our agriculture happens. We have subsidence that occurs due to groundwater withdrawals over pumping. Before I get to the subsidence here, I want to talk a little bit about, I have an example of Lake Chad in Africa. So if we zoom over to Lake Chad, this is an area, it's pretty dry. This is, let's go back here to 1963. Lake Chad, all the dark areas here are filled with water. We come up to 1972. We have our blue areas, that's the water, the green is vegetation. We come up here to 1987 and look at Lake Chad. All we have is a lake in this small area. And then if we come up to 2000, even smaller, and you can see it's kind of stayed at a steady point from in the 2000s, decreased a little bit from 1990. This is a really dry area. People pump the groundwater out and divert rivers and streams in this area to try to grow crops. This Lake Chad is right on the edge of the Sahara Desert, which is expanding over time. So you have a couple of different things happening here. You guys are going to look at an example in lab as well. So we've got increased groundwater withdrawals from humans. So we're pulling groundwater out. So we're lowering the water table in the area because we're using so much. And because we're pumping it onto the surface, it's getting taken up by plants, and it's also evaporating into the air. We also have in this area a drying happening. This is a drought. The desert's increasing in size, so we're also having natural changes causing this area to become drier. And hopefully that doesn't happen in our neck of the woods. We're pumping a lot of water out of the Oglala Aquifer, or the High Plains Aquifer. Great if you're studying groundwater for your project. Great area to look at. Lots of groundwater withdrawals. It's a pretty big aquifer. We don't see major changes in surface bodies of water, but we're seeing major declines in that aquifer. Over in Georgia, every year they have every summer they have times where they can't water their lawns or wash their cars. There's a couple lakes in the area that decrease in level dramatically in the summertime because there's so much groundwater withdrawal. And with that, in some of these places, we can also have subsidence that is a direct result of over pumping. And here you can see this is Cook County, Georgia, how much decline they've had in the water table because of so much over pumping. And what happens is as you pump that water out, it's kind of supporting the structure of the subsurface. As you pump that water out, the grains of, and especially if it's loose sediment, they start to compact. And because they're compacting, we end up, if this is our start time, we're pumping tons of water out, we're decreasing the support to this loose sediment, and it compacts and drops the land surface. San Joaquin Valley, as you can see here in this photograph, we've got where the land surface was in 1925, where it was in 1955, and where it was in 1977. Huge amount of decline. Venice, Italy is another example. New Orleans. These places are all locations where we have increased removal of groundwater, causing the land surface to subside. New Orleans, we have 3 meters or 10 feet. Las Vegas, 3 feet. In this part of California, up to 26 feet. Pretty amazing, just insane amount of land subsidence. Another problem that we see is what are called cones of depression. So when we start pumping groundwater, so here's a well installed, we start to pump water, it creates this depression, and we start pulling water towards this well away from maybe other bodies of water. So here's a before picture. We have these 2 wells installed. We start pumping from the smaller one. This might be a house. This might be an industrial facility, a factory or something. We start pumping from this well. We get a small cone of depression. We're not pulling that much water out. It doesn't change the overall water table that much. So we start pumping from this bigger well, and what ends up happening is we have a major decline. We have pumping way more water out. It's deeper. They're trying to get a lot of water. Big cone of depression forming because they're using a lot of water. And you can see from the start here to the finish how much that water level has dropped. So we can have a major decrease in the local water table as well. And you can visit that website that I showed you before for more details. We can also we also see saltwater intrusion in coastal areas. So here's an example of a normal situation. We've got fresh water. It's less dense. It floats on top of the salt water that is in the ground. So we have this kind of boundary between the fresh and the salt, and you can get kind of brackish water along that boundary. Coastal areas are pretty popular places to live, so people move in, they install wells, and then here you can see wells installed. They start pumping water. If it's too close to the coast or they pump too much, they can start to actually suck this interface closer to their well, and they can get salt water being pulled up into their well. In groundwater contamination, what we see, so for saltwater intrusion around a coastal environment, this is kind of a natural situation. Here's our sea floor out to our coast. Fresh water floats on top of the seawater because seawater has a higher density. And we have this interface between the two. It can be kind of a gradient sometimes. Coastal areas are pretty popular, so people like to move there. They install a well to have water. They pump too much, or they put it too close to the coast, and they can pull that interface closer to the well and then start to pump out salt water instead of fresh water. So that people that live in coastal environments have to be pretty careful about where their water comes from. So groundwater pollution can have multiple different sources. Some of the common sources, we can have waste disposal sites, so things like landfills that aren't properly lined or configured. We can have manure from farms, agricultural pesticides, herbicides that can get into the ground. Septic systems can also be a source of pollution. And what happens is a lot of the liquid part of that contamination can then seep down into the ground and either get into the wells that are being pumped or into the nearby rivers. So for example, if we say had a surface spill, maybe fertilizer, septic system, it could also be similar feature. Well, we have a surface spill, that gets on the top of the ground, if it's allowed to sit there, it's not dealt with immediately, it's going to seep down into the ground. And depending on what it is, some, especially with gasoline, there's multiple different parts that are mixed together in gasoline. Some of it is denser than water and will sink into the groundwater, maybe disperse slightly. Some of it's lighter and will float on top of the water table. And in underground storage tanks, you can have a hole in your storage tank and it can start to leak, and the same thing can happen depending on what is leaking. Might float on the water table and might mix into the water table. Now, to kind of talk about cleanup, what do you do? If this is a kind of a hypothetical situation here, we've got different houses indicated by the letters, the stars, a chemical spill, and that spill is on the surface and it starts to seep into the ground. And here the water table is pretty close to the surface, and it starts to travel, and that the groundwater will flow perpendicular to the surface topography. So I have these topographic lines drawn on here, and that water is going to be flowing parallel to those lines. So you can see I've drawn this plume of contamination parallel to those lines, and then eventually it gets to the stream. So if this is dealt with immediately, this plume could travel all the way to this stream, and depending on what the subsurface is like, that movement can happen relatively fast or it can happen pretty slow. So depending on what your bedrock is like, your response time might have to be within hours or it could be within days. So what do you do when something like this happens? Well, kind of figured out which way the contamination is going to flow. If you know this chemical spill happens, you know the spill occurred, you go and you stop the source. So you figure out where it came from, you stop or remove the source, and then you're going to have to figure out, okay, which way is the contaminant going to move to? And because of the topography, we know which way it's going to flow to. And then what we can do is figure out, okay, who's at risk? Who do we need to warn? I would say A would be the first to warn. C would need to know. D, possibly. Depends on how much this plume disperses in the groundwater. And then we're going to figure out, okay, well, what do I need to do to get rid of this pollutant? Well, if the spill is not traveling really fast, it's moving pretty slow, maybe it only has reached A. What they'll do is they'll start to install a well where they will start to pump out the pollutant, and then install some monitoring wells around this site, maybe further downstream, maybe monitor the stream as well to see if that pollutant gets down to the stream. So if they put in a well, they can create one of those cones of depressions that we saw way back up here, so that all of the water is going to flow towards the well. So the contaminant will be pulled towards the well. So they can create an artificial groundwater flow direction temporarily while they're trying to get all that pollutant out of the ground. And you can see sometimes, depending on how deep you're talking, what the water table is like, sometimes these pollutants might move within a year, sometimes it might move in 10 years, sometimes 50 years. So depending on what your bedrock's like, how deep the contaminant goes, you're looking at a variety of time frames. And you can look in your textbook for more information. So those are some of the hazards and aquifers. So we'll stop there and I will see you in lab.